Good evening, everyone. So again, my name is Jeremy Powell. And so far tonight, Michelle and Tom have both done a great job at showing how Antarctica and its climate and geography have changed drastically over the past millions of years. I'm going to continue on with that story, but talk more about how South America and Antarctica separated, and then how having an isolated Antarctica really affects global oceans and circulation and total climate. So this here is just a nice picture, actually, of the Drake Passage. You see some giant petrels that decided to join us for our trip. So what is the Drake Passage? Well, geographically, it's the gap in the ocean between Cape Horn, so the southern tip of South America, and the Antarctic Peninsula. But as a geologist, I'm more interested in the tectonic definition behind it. So tectonically, the Drake Passage is where the Scotia Plate, which we see here in red, separates the Antarctica Plate to the south and the South America Plate to the north. What this does is it allows for the formation of this circumpolar current, or the Antarctic Circumpolar Current, which moves all the way around Antarctica. And this is the world's largest and most powerful current. If you do the math, it adds up to being more powerful than all of the rivers in the world combined. So a very powerful current. But what does it look like? Well, my first picture was a bit misleading. Historically, the Drake Passage is known for having some really, really rough waters. So this is from our second crossing. Yeah. Sorry, I should have prefaced this. I didn't mean to cause any heart attacks. We were inside at the time. This is behind we are behind a glass window. We are not outdoors, so totally safe. We weren't allowed outside. But as you can see, the waters are really rough. In fact, they are some of the roughest waters in the world, if not the roughest. And this is caused because we have these really strong westerly winds that are moving off of the western side of South America, pushing through this narrow gap between South America and Antarctica. So really rough seas. And these same winds that are causing those big waves are also creating this Antarctic Circumpolar Current. So the current is totally wind-driven, and again, these winds are so great that the current actually extends all the way down to the seabed. So it's pretty drastic. Here we can see modern ocean circulations, and we can see that the Antarctic Circumpolar Current, so just along the bottom here, is really the only thing that is feeding all of the oceans into another. So it's imperative nowadays for global ocean circulation. It really aids in the exchange of water. But this hasn't always been the case. If we rewind the tape 40 million years, we can see that Australia is separated from Antarctica, and there is some flow that's occurring around, but the Drake Passage hasn't opened up sufficiently yet to allow for water to go through. So instead, flow is diverting to the north. So we don't have this same circulation. We don't have the same climate in Antarctica. It's a bit warmer. So understanding when the Drake Passage opened up is really important because it allows us to reconstruct global paleoclimate, so what the climate's been like throughout the past of the Earth, and global ocean circulation, or paleo-ocean circulation, so what our oceans have been doing throughout Earth's history. So the Antarctic Circumpolar Current. We can't think of it as just one uniform current. It really occurs through two main jets, and these happen at the subantarctic front and the polar front. And these fronts really just mark major oceanographic breaks, so changes in salinity and temperature in the waters. The main one is this polar front, because it marks a drastic change in temperatures between colder waters of the Southern Ocean and then warmer waters to the north. So if we have this Antarctic Circumpolar Current here, we can draw on the polar front right here. And what happens is as these cold waters move off of Antarctica and they reach the more temperate waters to the north, they sink below them. So what we have at the surface is this dramatic change in temperatures from warmer temperate waters to the colder waters to the south. And if we just produce a figure that shows surface water temperatures, we see these warmer temperatures, so around 10 degrees or so, to dramatically colder ones, 0 degrees Celsius. And what this does is it allows for the thermal isolation of Antarctica. So it has its own climate to itself. And this allows for the growth of the ice sheets, maintaining ice sheets. It allows for formation of sea ice and all that sort of stuff. So it's really important for our current climate nowadays. So yeah, the waters are cold. We had the chance, the privilege, I'll say, to go do it. I can't really speak for the rest of the group, but I'm not really smiling. My face is, it's actually frozen into position. And just take a look at our feet. It was very cold. It was fun, I'll say, but very cold waters. So another effect of having this thermally isolated Antarctica is the production of sea ice. So in the winters, Antarctica produces a lot of sea ice. It can form as far as the polar front, so it effectively doubles the size of Antarctica. And as this sea ice forms, what happens is, as the water crystallizes into the ice, salt is expelled and it concentrates in the waters below the sea ice. So we produce these really dense waters just below the sea ice, which then sink. And they're so dense that it actually creates a current, which we see here, this deep, cold, and salty blue current, which then moves throughout the rest of the ocean basins. So these dense currents that are produced, or these dense waters that are produced off of Antarctica, feed into the rest of the deep waters throughout the rest of the world. And this is important because not only are they salty and dense, but they're full of oxygen. So it provides oxygen to the rest of the world's bottom waters. And again, just having oxygenated bottom waters is important for the ocean's health. So when we have nice oxygen-rich waters at depth, we have very healthy oceans. So how did the Drake Passage open? As we've seen so far tonight, it's a fairly recent event in geological time, only 50 million years, so pretty recent. But as geologists, we're interested in the processes behind this. So this is the modern tectonic setting again. We have the Scotia Plate in between the Antarctica Plate and the South America Plate, and we see that again right here. If we go back 30 million years, the Scotia Plate doesn't exist. We have an older version of it called the Magellanus Plate. And Antarctica and South America are still connected. So what we need to have is the production of a divergent boundary, or a spreading ridge. And that's what we see here, with the production of the West Scotia Ridge. So this forms, it's creating a new oceanic crust, and it's pushing away the two continents. So this allows for the configuration we have today. And tectonism is still active. We see here all these red dots show earthquakes. So we're still having subduction, so a convergent boundary, of the Scotia Plate underneath Antarctica. And with this, we're producing lots of volcanism. So with the volcanism, we're producing a chain of volcanic islands. But we'll talk more about that later on. So when did the Antarctic Circumpolar Current commence? Well, we can look at plate tectonic reconstructions, and we can figure somewhere between 20 and 30 million years, or 30 and 40 million years. But what actual hard evidence do we have to determine when exactly the current became active? So there's many different proxies we can use for this, but I'll just talk about microfossils. So microfossils are microscopic organisms, and they're so abundant and diverse that we can actually use them to give exact ages of sediments, or age ranges of sediments. So here we have several examples of a type of microfossil called diatoms. And you can see they all look very different. They're definitely distinguishable. And each of these different diatoms would have an age associated with it. So we can use these in two ways. We can look for erosion of the seafloor. So if we assume that sediment is going to be deposited continuously out of suspension onto the ocean floor, then we know that once this Antarctic Circumpolar Current starts, it's going to scour away that material, and it's going to erode a lot of that. So if we look at the rock record, if we look through sediments, and we try and see if we can find an age gap in the time recorded through microfossils, we can get an idea of when that erosion occurred and when the current commenced. Another proxy we can use is looking at the actual chemistry of these microfossils. So with these diatoms, they produce their shells out of a material called silica, or silicate. And this is indicative of really cold waters. Whereas another type, foraminifera, have calcium carbonate shells. And this is more in line with warmer waters. So in the modern setting, we have lots of silica concentrated around Antarctica. This is called the opal belt. And again, it's a reflection of how cold those waters are. If we were to go back in time before the Drake Passage opened up, before the current commenced, and before we have a thermally isolated Antarctica, we can expect this opal belt is going to shrink. And once it shrinks, we have warmer waters around Antarctica. And instead of producing diatoms, we're going to produce foraminifera. So if we look back at the rock record, we can just take a simple graph. Don't be scared. It's pretty easy. It's just graphing calcium carbonate. So at the bottom, we have almost 100% calcium carbonate, so lots of foraminifera. And as we go through time, this changes. At 42 million years, we begin to have a mix of calcareous, so forams, and siliceous, so diatom, oozes. So here we're seeing cooling, and this is associated with that opening of Australia from Antarctica. It's at 26 million years that we see this dramatic change from lots of calcium carbonate to almost no calcium carbonate. So we see drastic cooling around Antarctica. So this is likely when the Drake Passage opened. So just to summarize, when did the Antarctic Circumpolar Current commence? When did the Drake Passage open? Well, we can get a whole bunch of possible dates through these proxy methods. It's still heavily debated, but likely sometime between 34 and 26 million years ago. And why is that all important? Well, once you open the Drake Passage, once you kickstart that current, and once you thermally isolate Antarctica, you have all the ingredients to produce the continent that we know today. Thank you.